let's get started. So welcome to the LTI Colloquium. We're fortunate today to have Ricardo Baeza-Yates from Yahoo Labs here. Rick is one of those people who's done pretty much everything there is to do in IR. He's a well-known textbook author. He's been a professor at 2 universities and still supervises PhD students. And he runs 2 of Yahoo's research labs. In his research, he does everything. It's just daunting when you think about the range of things he does. In his research career, he's looked at everything from very basic computer science, data structures, and algorithms kind of research to work on distributed search engines and large-scale search engines, which we'll hear some of today, and also looking at query log analysis and analysis of user behavior in social networks. So he really covers a wide range of research, and we're very fortunate to have him here today. So, and Rich also great to be here. So it's great to have him, and please welcome.
Thank you very much. First, I want to thank the invitation of Jamie and Jaime to be here for the first time in CMU. I went to visit the department a long time ago, but never had a good reason. So this is basically we cover like 6 years of research, 7 years of research to try to find a new kind of search engine. So this will be the main topic of the talk. And it's a real distributed web search engine. Most of this work has been done in the recent years with Bertrand, Barlock, and Masoglu, but a lot of people have contributed. You will see some of the authors in there, most of them from Yahoo Labs, but some of them were students or collaborators. So we're talking about many papers, and talking about this, I said, okay, I should put the story, because the story is long. So I will start. Greg Murphy is really attacking. So we'll take a research story. So I wanted to change the architecture of a web search engine. So we have to work on architecture. But that means looking at caching, looking at document replication, looking at query processing, looking at indexing, looking at crawling, because everything is important in web search. So basically, this is the summary of this story. A very long story. Many papers. One was the best paper award, the basic architecture. But you see, we have been working all this, and finally, we are putting everything together. And this is a paper from one of my master's students will present next week. So this is the end of the story, and now we have to wait until we can build this search engine. But you will see we have some prototype right now. So I will go very fast because I have a lot of material I want to cover. But basically, I'm sure you know web search. So this is a classical information retrieval system where a person sends a query, gets some good answers, some bad answers, some missing answers, and with a small document collection. What are the new things in the web? Huge collection, no information needed all the time, just a need. So different kinds of queries. Navigational queries, transactional queries. You are not really looking for information. And then the context is very important. What are you trying to do? Because that maybe will change the ranking, will personalize your experience. Maybe it depends on the device. You are not using a computer, you are using a mobile phone, and so on. So that's the problem. And really, web search is one of the most complex data engineering problems today. For many reasons, here are the main ones. Distributed in nature, that's part of the web. We cannot change that, that's good. The web content is distributed in many servers, more than 200 million servers. Large volume of data, that will be a different topic, but in fact, you can generate infinitely many dynamic pages. So you can crawl forever if you want. And a very highly concurrent service. Billions of queries per day in all the search engines currently running. And of course, people expect very good and fast answers, and for free. Because if you have never paid for something, why do you pay now? That's the problem. So very hard engineering problem. You want good answers, and you want them without any cost. So the current solution is replicate a centralized system, and we will get more details of that. But basically, just to start, I want to borrow a nice figure from a paper by Moffat and Sobel, 2004, so 10 years now. But I adapted for the case of web search. So basically, you have two problems, scalability problems that you have to deal with. So you have to deal with data volume, that in web search means a larger and larger index, and in the other dimension, you need to deal with more queries per second, because you have more people asking, and so on. So let's say you have one cluster where you solve a problem for certain data volume, certain throughput. Well, if you need more throughput, the solution is easy. It's called replication. Very easy. You just copy your system as many times as you need, maybe different locations, geographical locations, and you get what you want. Scaling the data is a bit more harder because you have to do partitioning, and there are many ways to partition data. The optimal way probably would be NP-hard, depending on what you try to optimize. But then you can do it, and basically you can copy the same system, same software, but different data, and you have to change the query processing because you will need to send the query to maybe to more than one place. But you can solve it, and you get the right number of clusters. So these are the two problems we have to solve just for dealing with the scale, replication and partition. So caching is one of the main things that will allow, it's like steroids, will allow the system to perform much better in a single cluster. So using caching well, we can double the capacity of a search engine, especially on the throughput side. So basically you can answer many more queries because you are having the data in the right place much closer to the user. So I will focus on that later. So basically you need to optimize this single cluster to the maximum possible capacity using caching and other techniques, and then you do this game of replicating clusters along the two dimensions. And if you think, it's very interesting, this game of caching and replication, because let's say we want to keep some documents, part of the index, or the answers, already stored. We can do that in a static way, so we can pre-compute some good set of answers and having them ready, because most people is issuing the same queries. Or we can do it dynamically, like in operating system, we can learn how to cache and so on. So for documents, this is called always replication. I don't know why it's called more replication than caching, but basically if you are doing dynamic, it should be caching. However, for the index, if it's static, people will call replication, but if dynamic, they will call it caching. For answers, it's caching all the time. But basically, you are doing the same thing in most cases. You are basically duplicating data or pre-computing data in a different way, so you have it ready to do something. So maybe the only difference is that in some cases you duplicate, in some other cases you pre-compute. But basically, you are doing the same. So this is more the real current search engine. So this would be a typical architecture. So you have caching at several levels. You cache answers, you cache index, you cache documents, you do replication to improve the throughput. You do parallel query processing, you have partitioning index. So here you have the search clusters that take the queries from the front ends and the proxies that come from the users. So this is the online part, this left part, and everything that's in the right is the offline part, basically crawling the web, gathering data, parsing it, extracting new content, new links, and sending it to the indexer to build the index. So this is the typical search engine. Of course, there's a lot of engineering. And basically performance, after you know the basic concept, is just engineering, how to do something faster and more scalable. So if we use this basic architecture, we can have different architectures. For example, here you have the purely centralized, You see there's only one box around all the servers, so it's just one cluster. Or you can replicate in different places. So basically, this is the case where you're replicating on the vertical axis, so basically you are having higher throughput. Or you can do both, replicate and partitioning, and then you can handle more data. So you see that here, this that was for just one box is split in several boxes. So where are the differences? Well, how many data centers? How will I assign users to data centers? So basically, which cluster will answer your query? And also the assignment of the index to the data center. So basically, which center will have your document if you are a website. So let's do some quick envelope computation. So let's say I want to do a small search engine, only 20 billion web pages. If you compute the average size of that, that will imply at least 100 terabytes of text. We are only indexing text. Let's assume this is design. If you have a normal processor with a normal, say 8 gigabyte RAM, you will need at least a cluster of 10,000 nodes just to hold the index. And let's assume that in that cluster, we can answer 1,000 queries per second. You will think that this is really slow for having 10,000 nodes, but remember we are partitioning the data, so every processor is answering all the queries. So we have 1,000 queries per second per processor, because we're distributing the data, we're using parallel computation, and I will assume that merging the answers is very fast. So suppose you need to answer not 1 billion queries, but you need to answer 350 million queries per day. That will be about 4,000 queries per second. But of course, by Murphy's law, the load is not uniform. At some point in the day, you have more queries. At night, you will not have so many queries. So let's say that you want to be prepared for peaks on the load, and also you want to be safe, so have some fault tolerance because servers may go down. You may have some problem in the data center, and so on. So let's say we have a margin of 3. So we want to be able to answer 12,000 queries per second, and then that means that I need to replicate 12 times to get that, because basically we have 4 times 3 equals 1,000 queries per second. So in this case, with 12 big clusters, maybe in different places, so to have more fault tolerance, we're able to have this search engine. Well, this is not cheap. Maintaining this system is not cheap. If you extrapolate, you can do your own numbers. So take 100 billion web pages, 1 billion queries, you will see that this number is completely not sensible to what we would like to do. So I say, well, why do we need to do this? Why we don't do a real distributed search, and maybe we can use less resources? We'll be closer to the websites, we'll be closer to the users, we may answer local queries locally, and so on. So the main problem of distributed search is the network latency. Internet. You cannot have dedicated links for this, it will be too expensive. You need to use internet. Maybe a very good connection, but still will be the normal service that you find today in internet providers. The best service, but still limited. So how do you deal with network latency? So that's the main problem of this architecture. And what I want to show today is that we can do it. We can do it cheaper, without sacrificing anything, with almost the same response time and the same quality. So basically, we will compare to the centralized architecture. And for that, we need a lot of things. We need caching, we need new ways of partitioning the index, we need to exploit locality. Very interesting. We need to have prediction mechanism, machine learning-based prediction mechanism, to look ahead and do things in advance to do it faster. So these are some advantages in addition to that. So we can have higher concurrency. Maybe we could exploit the network topology. I have found only one paper that tried to exploit the network topology. Remember, the web topology is not the same as the network topology, and they are not correlated at all. So that would be an open topic. But very important, there are many external factors that you cannot control. And that's my problem. You cannot control users, you cannot control how data changes, you cannot control the quality of the internet links and so on. You have to deal with that. And because everything is interconnected in your system, one mistake from one programmer can make everything useless. You need to be very careful about the choices that you take. So what will be the challenge? So we want to return the same quality resource as the current search engine. We want to be as fast as the current search engine. We want to have high capacity. We want that to be dependable, so everything about availability, safety, and security, and we'll talk more about that, and not be scalable. These are the challenges of any search engine, and we want to keep that in the distributed one. So let's start with the first model that we'll talk very little because we have less research here, but this is not a crucial part. But basically, crawling is a very hard scaling problem. You need to distribute many threads on many servers to gather data from many different places in the web. Very hard to optimize, very hard to evaluate, because basically you need to have the same internet to evaluate, and that's impossible. You cannot have two crawling algorithms running in the same internet. If they run at the same time, it's not already the same internet. But this is better because it's closer to data, you use less network, and you have less latency. So we have done experiments and that show that this is better. But I will skip all our research in crawling because it's not so interesting. But just to give you an idea of the external factors, crawling is the one that has more external factors. So this is just to have an idea of how many different external factors we have. So you have the external factors here, like web change, web growth, site behavior, spatial locality, and then you have all the things you have to worry about. Quality, performance, politeness, you cannot go and attack websites, implementation issues. So this is more or less the complexity of the problem to write a good problem. But I will skip all that. So I will not talk too much about document partitioning. I assume most of you took Jamie's course in IR. So basically document partition means slicing this vertically. So for example, one processor takes care of the index of documents 1 and 2, another 2 and 3, and the other one 4 and 6. Of course, the vocabulary is small enough to fit in memory, so that's not the problem. And then you can do also term partitioning. It's not used in practice, but basically you can do like horizontal partitioning where one processor takes care of the first 2 words, next 2 words, and then the third, the most frequent word, and so on. So, what is the comparison of these 2 ways of partitioning? Well, they are not difficult to partition. One advantage of term partition is that you can have concurrent queries, so you can have really parallelism on the query processing, but it's much complicated to have a good balance, and the worst part is that it's very hard to maintain. You need to build the complete index, you need to update the complete index, while if you have document partitioning, you can build local indexing. And that's the main reason most systems still use document partitioning. One possibility would be to use term partitioning at the local level, and then document partitioning at the global level. And we have practice with that. So this would be a real partitioning, could be completely geographically based, like in the top, or it could be a bit better, language based in the bottom. So for example, blue is English, yellow is Spanish, this kind of a dark green is Portuguese, light green is Arab, and so on. So this may be the main open problem, because if someone comes up with an interesting parallel algorithm that, I don't know if it's possible, maybe not, you can get linear time distributed indexing, then maybe we can do much better partitioning. So that is another problem. It's a good PhD thesis. So these are the 2 problems I will not touch in the next half of the talk. So caching. I assume you know what's caching, right? So I don't need to explain it. We have studied a lot about refreshing caching, because we have to refresh the answers, because maybe there's some mistake results, but I will not talk about that. That's an interesting problem, but it's not a basic problem in the running architecture. So another thing you can cache is the index, where you can cache inverted lists. So the first question is how much of your resources should be devoted to cache answering, cache of answers, and how much should be devoted for the index. And this is the problem that 6-7 years ago, no one had really had addressed well. Second question, should be a static caching, or should be only a dynamic caching, or should be mix of both? And caching is crucial because you reduce the latency and the load of backend servers. So this was the first paper that was looking at conceptual part of caching. And just to give you an idea of the kind of distribution you see in the web, here the data we used at that time was only the UK collection, so basically all documents in the United Kingdom, all queries in the United Kingdom, and here you see what happened. So for example, here you see the query distribution, it's a perfect power law. Here you see the query term distribution, more bias, another power law, and here you see the term distribution in the document collection. You see it's almost the same power law. So interesting, the distributions look similar, worse in queries, worse in the content. However, the correlation is low, 0.4. So this is something that I knew, but I knew at a small scale, and I had again, I would have validated this many times. The correlation is low, between 0.4 and 0.6. And this is very interesting because it has another connotation. It's basically what you write is not what you search. So if you're expert of something that you search, please write about it, because then you can get a better correlation. But basically, people is interested in things that are not in the web. So otherwise, the correlation will be much closer to 1. So okay, what we should cache? Well, the first problem is the queries are very biased. So the graph here, you see that there are many queries that are basically unique. And the truth is that you take a typical query log, 50% of the queries are unique in a time period. So basically only one person posts that query to a search engine. And this is really bad for caching because that cannot be reused. So basically the best you can do while caching answers is 50% hit ratio, because all the other ones are unique. On the other hand, if you look at query terms, which would be the index caching, only 5% of the terms are unique. And this is another very interesting thing on queries. People is using the same words to write different queries. The caching in the index will be 95%. And I guess that explains the diversity and the exponential number of combinations you can have in queries of 3 or 4 times. So infinite cache here is a 50%, infinite cache here is 95%. So we tried a new algorithm that basically was, okay, the simple idea is to cache the things that are more frequent. However, in the index that's not a good idea, because maybe there are things that are very frequent, but also they take too much space. So we have a knapsack problem, and then we use the standard well-known solution for knapsack. We use the ratio between the frequency of the word in the query divided by the frequency of the document, of the word in the document. So basically, you want to have things that are frequent, but they are not too long in the index. And then we try different algorithms. So we try static caching, we try dynamic caching, we always also try dynamic caching with this new idea, knapsack, and we got this. And it was a bit of a surprise, because basically the best was this static knapsack, but by far. You see the hit rate? Hit rate was almost 95%, which is the best you can do in an int. However, the others were not too good, and the second best is where the tie between LRU and LFU. So we couldn't help the operating systems people that don't know which one is better. For us, it's also the same, and they are good. But these are dynamic. So first answer, cache should be, the answer cache should be static, and the index cache also should be static. And then you can update it periodically. Okay, so now we know what I'm going to use, but I still don't know which fraction should go to answers, which fraction should go to the index, and these are the two curves. So this is the hit ratio curve. So this is one of the cache of answers. In the infinite will be 50%, and this one is the cache of the index. In the infinite will be 95%. So of course the solution would be here if the time that you take to get that data is the same, but that's not true. The answer cache is much, much faster than the index cache, and then the optimal is to the right of that. Now that says, for example, 30% should be devoted to answers, and the other 70% for the index. Well, we did full implementation of this. We tried two different configurations. This is the centralized index. So basically, you see that the optimal was about 10% in the compressed version, so that means around 20% compressed version of the index. And if you do distributed system, well, what's the problem here? The problem is that the index cache is in a different server, it's remote. So it takes even more time to get the answer. So here was the opposite, was more like 70%. So in one case was 20% centralized, went to 70% distributed. So things change a lot depending on the architecture. Well, you may argue that if you use static caching, you will need to recompute too often the cache. Well, we thought the same, but then in fact it's not true. We took one full year, we took windows of 3 weeks, and then computed the correlation of that window for a year, and the correlation was always higher than 0.995. That means that even if you have bursts of queries, the background of queries is so large that any burst is like noise. So you can have 1 million queries because of the social inputs, but you have 1 million queries of everything else. So you don't need to compute this too often. Even once a month will be okay. So why caching really doesn't help beyond that point? Why we can do better? Well, one problem is that you can see that caching results takes the top of the distribution. Then caching the index takes the next part of the query, more or less. It's not exactly like this, but just to understand. But there's a big problem. There's so many unique queries that maybe you will go to the dynamic part of the cache. That way they will pollute the cache. We should have something like say, do not cache this. We will never see this query again. Don't try to put it anywhere. It's useless. So here we have the first idea for a prediction algorithm. Can we predict not to cache something before we execute the query? Very important, before you execute the query. We had an intern doing this. She was not clear about that, and she did a wonderful mechanism to predict, but after executing the query. Okay? Well, that was an extra paper, but what didn't solve the original problem. So, basically, within the admission control cache, where you have a small machine learning piece that will say, you can enter. No, you shouldn't enter. Like the guys in the front of a discotheque that look at your shoes and say, no, you cannot enter, running shoes are not allowed. But it's not the running shoes, it's that it's like you. Right? It's completely arbitrary. It's a bit better, we're trying to learn. But basically you have two parts, the control cache and then the dynamic cache because you may have worse queries. I will skip this, but basically we improve the caching. Here we are different query blocks, and we could improve about 3%, which would be like 5% more throughput, which is interesting in a search engine. Well, what's next? Well, if you do caching of answers, the distribution that will reach your search engine is not the original distribution. So basically, after you cache the answers, you will get a completely different distribution. How different? Well, this is a sample of queries, a very large sample, and you get the distribution. So most of them have 2 terms, and then 1 and 3 are tied, and so on. But if you cache answers, we take the most frequent queries, the average number of terms goes to 3.2. So basically, the answer cache takes care of most of the singleton term queries, and then the distribution after is completely different. In fact, the mode here is on 3, not on 2. And you have to take that in account if you want to do the index caching. And this was very important because some people were saying, okay, let's do some kind of a small version of the index. Let's prune the index. And we found out, and I'm going to skip all the details, but basically that was, I guess, one of the very few negative papers in CGIAR that we showed that index pruning doesn't work because caching is doing basically the same. Caching is basically dynamic index pruning. And then the result was that don't bother, don't use it. So we forgot about that. Okay, let's go to the traditional index and keep going. Locality. If the query can be answered locally in the local cluster, that will be the best situation. It will be faster. We are closer to the user. Nothing else to do. And then we said, okay, can we predict if the query is local? And we have this tier prediction paper. So we want to predict if the query is local without looking at the results, and also without increasing the extra load in the next level. And you will see why. And this can be applied to centralized search engines, for example, search engines that have 2 indices, one good, fast index, and one bad, big index for the rest, and also in the distributed settings. So, how we can do this? Well, instead of searching in the first index and then send it to the remote index, we could do it in parallel. Let's send the query to both indices, and then we have the answer faster. That's true. However, now we are doubling the load of the search engine because we are sending every query to 2 different places. We don't want to do that. So the idea is predict where to send the query. And this is the generic scheme. So basically we have 2 indices. Could be fast and small, slow and big in a centralized architecture, or could be local and fast, remote and slow in a centralized, in a distributed architecture. So this is the same scheme for 2 different architectures. So here's the predictor. We'll say this query needs to go to the other index. So the green line is the standard path. All queries go to the first index. You need to have some answer. But then we can predict, and the blue path is that the ones that we predict need to go to the second index. So let's assume that F is the real fraction of queries that should go to the second index. If you were an oracle, you know the answer. However, the predictor is not perfect, so you have F minus false negative plus false positive. False positive is extra load in the second index. So things that you send there, but you didn't need to send there. But you have to deal with that. False negative is when the result assessor looks at the answer and says, wow, I can't answer because I need answers from the second index, but we don't have them because the predictor did a mistake. So basically, in that case, you need to tell the corpus predictor that made a mistake, and you can learn from that, so you can learn in time. And then do the query to the second index and merge at the end. So this one will be the only ones that are answered in sequential time. All the others will be just the first index or in parallel. So we implemented this. So we had predictors. You see in a centralized case, the prediction was not too much better, but you get very high precision. In this distributed case, the prediction is much better, and you have very high recall. Why? In the first case, we basically used just English text. In the second case, we simulated a language division, and we had one corpus in Spanish, one corpus in English, and then it was much easier to predict that case. But that would be a realistic case, because when you have a distributed web search engine, you will split by language. You can do analysis. I will not go into analysis, but basically you assume that the cost of running the query is proportional to the size of the index, and then you get some conditions that must be fulfilled, so the extra cost you pay is worth the savings on time in the architecture. And just to give you two examples, in the centralized case, let's assume that system A is twice faster than system B, but system B costs twice the cost of system A because it's much larger, it's a larger index. Well, centralized case, you can get 29% faster answer time at 20% extra load, and then extra cost. Distributed case, much better, 50% faster at just 0.5% extra cost. Well, in both cases, it's worth it. Even in the first case, if you can do 29% faster, that means you can answer more than 35% more queries. That's good. That will give you more money too. Remember, search advertising depends on the traffic. And then we go to the architecture. Although we didn't do these things in this order, but we are working in parallel on the architecture. So the architecture is logically very simple. You have a start topology where you put the most loaded center in the middle, and then you have links, logical links to all the rest. And the idea is the local queries will be answered locally, and then global queries will go to the rest of the architecture. So we'll skip this. To evaluate if we could do it cheaper, we need a cost model, so we need a simple but realistic cost model. And basically we'll say, if the percentage X of queries are resolved locally, and we know how much is the cost of power, today the main cost in search engine is power, and it's not the computers, it's their conditioning, but that's it. And the cost of internet, what will be the optimal solution? And here this graph is basically different locality ratios and the number of sites. And we can compute the optima, which is the optimal number of sites depending on the ratio of the cost of power and energy. And basically, the number of sites is between 5 and 10. So we're talking about few sites, but should be distributed. Now, these two lines is the ratio that was in 2007 of the cost. This is 2008. So because the price of energy is not going up and down, but the cost of internet is going down, this line is going to the right. So basically, it's going toward more distribution. And it was another signal that, okay, we have to worry about distributed search. So how we process here? So we combine many things, and I will skip this because then I want to show the last paper that basically put everything together. But basically it was a simple idea. You have local and global statistics, and you have the simple structural score to send queries to other places. So it was a very simple algorithm. Doing some document replication, doing caching, of course. And when you do caching, when you do replication, what you're doing? You are increasing the fraction of local queries. Basically, local queries is an artifact that you can tune by using these techniques, putting more things local, so things that people look, they look local. And we got these. So these are curves of different locality and depending on the architecture. So this is the basic with caching, and document replication, losing a little bit of the precision of the search engine. So basically here, what one means, I will allow the search engine to give one result different from the centralized architecture. And you can go all the way to basically have a completely different search engine. But you see that's how locality changed. And the good thing is that the first number were very good in the sense that with, say, 20% difference, that doesn't mean 20% loss of precision because maybe the answers are still good. We could do the same cost. Later we improved this paper and we showed that BCG was less than 1. So basically we could do this with less resources. So basically having the same answer with the same response time, but using less money. So then there was a series of papers that improved this. For example, Barla did a very nice LP formulation to improve how to send queries to other sites. But of course, I thought that in practice it was much better to use a machine learning-based prediction, but we didn't know. So we, for example, the first paper had a 10% improvement over the basic architecture, so that already was what I mentioned, that was cheaper and equivalent to the centralized search engine. We did a real system, so we had machines running in several places. Right now we have in Singapore, Switzerland, Spain, Chile, the US, and Turkey. So we know the real numbers of all these, so we can simulate it. We cannot run this for long, but we can simulate this, so we get the right numbers, and then we build the next simulator. And then we said, and I will skip this, let's put everything together. So here's some results on partial replication and subcaching, but let me go to the final step. So this is, okay, let's put caching, let's put replication, but now let's use machine learning to predict where to send the query, and not to every server, but to just the right server. And we can do that because there are not too many places. We're talking about 5, 10, we're not talking about 100. So we will measure average query response time, result quality, and query locality. So these are the three things. We want to have the same response time, we want to have the same query result quality, and we want to have as many queries as local as possible. So we simulated this. These are all the possibilities for document replication. So basically, no replication here. Replicating the same everywhere. Replicating differently. Okay, and here another variation. Basically, this is a global value, this is a local value. So each server decides how much to replicate. These are 4 possibilities, and here you get the different curves. So this is the basic one, which is not very good. But then if you do the last one, this is the best. You get the red line, and this is the fraction of queries that are local. And this is the replication percentage. So this is the log graph here, the linear here. So basically with, say, 8% replication, looks like more than 50% of the queries are local. So you can answer them in that cluster. Okay? So this was the full analysis of replication. Then, query forwarding. So we want to send this to only some sites, and what we'll do is we'll build a predictor for every pair of sites. So we'll use the entire prediction idea, but now between pairs of sites. So in every site, we'll predict if we need to send that query to every other site. For example, here will be only 3, maybe it will be only 10 predictors per site, but that's okay. It's much better to have local predictors than one single global predictor. So we take a binary classifier for every pair of sites. We consider features that are pre-retrieval, post-retrieval. We also include information about the performance of the query on search sites. And we also have a parameter, which is a confidence threshold C, to send this to a different site. So basically, we have a pre-retrieval classifier, reference threshold. We don't send it, and then we do it locally, and then we do a post-retrieval classifier, and if we need more answers, we send it to the remote server, the ones that we need to. So basically, the same idea before, but applied to pairs of servers. So here are some results of what happens with machine learning. So first nice thing is that the accuracy was much better than the linear programming solution we had before. So machine learning, as I expected, was better. And of course, if you have replication, is the best. So here you have no replication, and here you have 8% replication, and this depends on the confidence threshold. So the linear programming processing algorithm was the baseline, because that was best known before. So what are results caching? Well, we can have basically 4 different caching strategies. We can have a local one, so each site caches their own local results. That was the baseline, the simple one. Global, all sites cache the results of all queries. This will be better, but not so efficient in the use of space. Partial, the query results are cached on some sites, and forward, we point to other sites that own the result of the cache. That's still faster than trying to process the query in a server. So here you have the results. So global, of course, is the best, local is the worst, and then partial forward is in the middle, and resource-wise is much more convenient, so we can use that and we don't lose too much. But look that we have very high hit rate. It's about 50%, and this is valid for, say, 240, which means the result is valid for 2 hours. So I'm not talking about refreshing, but basically TL means a measure of when you need to refresh your cache. Usually, the cache is refreshed, say, per day, so about here. So the final system, putting all this together, we will have a trade-off between quality and time. So here we have NDCG, so I hope you know what's that. You will look to Dennis course or any other future course with no discount community gain, so normalized discount community gain. And here there are all possibilities. So no cache, global, no replication, machine learning, linear programming, and the Oracle. The Oracle is the one that knows everything. And you see the Oracle is the best, but of course it's the Oracle. But you see that you get a very nice trade-off between quality and average response time in milliseconds. So this is the best. This is the ML with global caching. Basically, you can answer losing only 1.5% precision to the Oracle in less than 200 milliseconds. And this was the final result of putting everything together. So if I had the money, I would get this. It's expensive. But at least there is one possibility to scale, really to scale, and much better than a centralized search engine. So conclusions, I think I want to stress the importance of caching. Caching is really important. I want to stress this concept of local queries that you can tune using different techniques. So local queries is something that you can decide how much is local because of caching, replication, and other techniques. Very important, we can predict very well where to send the query to get more answers. So you don't need to overload the system, sending the query to all other remote sites when you don't have enough good answers locally. And here you saw these three different examples of machine learning-based prediction techniques to improve the search. And this is, I think, also very important because before these were like only used for ranking. The machine learning was for ranking, but not for doing other things. And the most important one, and this is something that you don't see in the papers, but I see it because of the experience we have in all the way to find the right system, is that you can't study every component alone. They are tightly coupled. So you need to understand what is happening. Like, for example, how the query distribution changes after the cache. What will happen with the index if you partition this way or this different way. So you need to understand the interaction between the components, and you need to understand all the trade-offs involved in that interaction. And this is the part that took more time, and that's why I guess it took 7 years to understand everything to do the final search engine. So I don't know if I went too fast, but if you want to go to Chile next year, we are organizing Stiga. Sadly, South America is here, so it's winter, but the still is not bad. It's better than this, for example. In winter, so no snow. So that's good, and almost no rain. And you can only go to the desert, Easter Island, or the mountain. I don't know, questions?
So you started off with these scary numbers about the number of machines you would have to have in order to index the web. And so now we have this much more efficient architecture with different documents in different regions of the world. And so how does that change things? I mean, you never actually type after that.
So that will decrease in a linear percentage, go to max say 20% the number of machines. But I think it's a direction to go to use less machines. I don't have exact numbers from the example I gave, that's a good point. I should have the number, how many machines I need now for the same architecture.
At least university people, those still seem like scary numbers. You're talking about billions of machines, right? So,
well, not machines, but processors, because you can have many processors per machine now. So yeah, search engines don't use really machines, they use racks of processors. So we don't need the screen, we don't need so just single slides, okay, here, there you go. 20 more, whatever. So, but that's scary numbers, that's why I was worried, because it's too much. So, search engines have, for example, more processors than many countries. That's scary. So yes, so I guess it's a kind of clean computing. I was worried that we should use energy better than before. For example, I haven't said anything, but the next step is rewrite all the search engines such that we use less energy. So energy efficient algorithms, we know that's possible too. And people is working on that, especially mobile phones. But if you can do it for decrease air-conditioned user by 10%, that's a very interesting result. And we have one paper about that. So Varga did a paper with some terms about power efficient algorithms in query processing. So that's another line, so very interesting line. So, oh, yes.
You said earlier on about putting the queries together from multiple sites and not really well. You want to say something about that? So if you send your query out to multiple, both locally and globally, you say putting the information together at the end is never focused for.
So the ranking phase.
Yeah.
Yeah, I mean, that is a small percentage of the query processing part. Because basically we are making different rankings. You have global statistics, but the real part is to access the index. Maybe part of it will be in disk or will be remote. Really, network latency is the thing that kills you. Imagine in a standard network latency, you can do a lot of computation in a standard network latency that you have today. Yes?
For the entire process, you have discussed approach across caching, partitioning, distributed systems. I don't see any part that we can use user-specific permissions to improve the precision.
It's a good question. So the question about what about the user, how we can improve that? Well, this was to build a new architecture, so the focus was performance, keeping the same quality. But of course, we have done research on improving the ranking, personalizing the ranking. So you can do that, all that on top of this. But the goal was, can you do the same search engine, the same, distributed? That was the goal. Now, but for example, you can do interesting things. So suppose you can do it faster. Okay? And in one of the papers, we were able to do it faster, but 20% faster. So you have two choices. You give that 20% savings to the user, so the user feels the things are being searched faster. And I don't know if you will notice 0.2 seconds. Or you can do better ranking. The time you save, you put it in doing better ranking. So you take time from one side of the system to give it to another part. And for example, we showed there that we could improve like 10% the precision just by changing time in different parts of the search engine. So that's another paper. I have it in the presentation, but I skipped it because I have too many results. So, but again, this is not about quality. We were trying to mimic the centralized result. But of course, there are many interesting problems on improving quality. Personalization in particular. Yes?
Thank you for the talk. It looks like your business paper will be very interesting. I have a few technical questions. When you scroll back to the slide where you have this back on the envelope calculations, I don't know how many. It wasn't somewhere at the beginning.
No. So you see how many hidden stuff you have. I was afraid I would talk too much.
Yeah, so it says 40 billion web pages and 10,000 nodes, right? So do I understand it correctly that it should be something like 2 million web pages per server, per node, right?
Let me, I was not working against it. Try the same trick before. Don't know why it works. If you have computer science, it works, but don't know why.
Okay, maybe then I should
It should come.
okay, I can ask another question that doesn't require the slide.
No, I have it here, so you can tell me what's the question.
Good. So it says 20 billion pages, 10,000 nodes, right? So it should be around 2 million web pages for a single node, right?
If you have it in memory, yes. It's assuming you have it in memory.
Yeah, I mean 2 million nodes, 2 million pages per node, right?
I guess so, yes.
Then why would you bother about caching any? Well, why would you bother about caching at this point? Because 2 million is just a very small collection. That would, like, say, 16 gigabytes, you can fit not only the complete index, but also the, say, zip documents for each of these 2 million documents.
That's true, but if you have it in the cache, the answer in the cache, that's much, much faster than doing anything else.
Right, but I
Because it is a speed, it's not that you should do it.
Yeah, but what I'm saying is that I can hardly imagine any like server that has now less than 16 gigabytes of memory, right? And 16 gigabytes of memory should be enough for 2 million pages.
I agree with you, but still, that doesn't mean that if you have the answer already pre-computed, that's much faster than trying to compute the answer.
Okay, yeah.
Well, that's the point. I mean,
And I have also another question regarding distributing the queries. So if you send, say, 1,000 queries, like the different sub-indices, do you just do it in parallel? Like
Yes. Yes, and for example, in this case, the 1,000 queries per second are going to the 10,000 nodes.
10,000 nodes?
Yeah.
And what if one fails or it takes longer to answer?
You usually will use, for example, some fails one bother, and you will never notice that one node is missing in the answer. So you can also have it by software. So we do all the fault tolerance by software. So if the machine fails, another one that is prepared to run with the same collection. So basically, you need to have replication. That's another reason to have replication. Basically, if you have one machine failing, if you have replicated, you just need to copy that to another machine, and the machine is ready, say, in certain time to replace that. And also because you have replication, if that machine fails, you can answer that query. Another machine that has replicated, you will increase the load, you will increase a little bit the response time, but still you will get the answer. So replication provides that too, all correct. Any other question or query with 2 words? All right,
Thank you, Rick.